Let's take a look at your quiz number 16 now. We start off with a big page of information here. It talks about a scanning electron microscope. You might be interested in that. You might not be interested in that. Regardless, our strategy when we see a big page of information like this is maybe skim it. Right? We're not looking for necessarily for details. We're not looking to necessarily understand every single thing that's in there. We're just skimming to kind of get the gist of it. And then we read the question. Once we read the question, maybe we can go back to that big box of information and find some more relevant information. Most of it, as you know, is going to be irrelevant, right? Not relevant. Let's take a look. Let's pretend we've skimmed it here. You guys already have. Maybe we see a couple numbers in there. By the way, if you do happen to see a couple numbers as you're skimming it, might be a good idea to draw attention to that, because odds are that's where you're going to go, right, is to those numbers. Numeric response number 1 says the magnitude of the magnetic field in the magnetic lens expressed in scientific notation is what? The magnetic field here, the only way we can calculate a magnetic field in physics 30 is to use a magnetic force. When I go back here, I'm looking for a magnetic force somewhere. There we are. A particular lens focuses the beam of the electrons. A particular electron experiences that magnetic force. All right, we're looking for the magnetic field strength. Let's say the magnetic force is equal to QVB. Let's rearrange this to solve for B. It's the magnetic force that we're given here over Q times B. The magnetic force is 3.31 times 10 to the negative 12 newtons. And we divide that, make sure you use the right charge here. It's the charge of an electron. And times that by the magnetic, should be the speed there, right? Should be the speed that we got on the bottom here. We're divided by QV, not by QV. 1.6 times 10 to the minus 19 times the speed, which is 2.65 times 10 to the 7 meters per second. We do that calculation, we end up getting a 7.81 times 10 to the negative 1 Tesla. 7.81 times 10 to the negative 1 Tesla. So we'd express that B times 10 to the negative W. We're just looking for the 7.81 in there. The radius of the resulting spiral of the electron's path. Well, normally when we see radius, talking about a charged particle moving in a circle, we're going to do Fc equals Fm, right? mv squared over r equals QVB. Except in this case, we already know what QVB is. So in this case, we are just going to say mv squared over r is equal to 3.31 times 10 to the negative 12, the magnetic force that we had already found before the last question. Let's rearrange this to solve for r. R goes up, 3.31 goes down. I get mv squared over 3.31 times 10 to the negative 12. Let's sub in some numbers here. I got 9.11 times 10 to the minus 31 times v squared. Don't forget to square that speed. 2.65 times 10 to the 7 squared. And then divide that by 3.31 times 10 to the minus 12. And then when we do that, math, we end up getting C, 1.93 times 10 to the negative 4 meters. Well, here's a good question, eh? It's been a while since we've seen this. A little toss in there. The collision that produces a backscattered electron is classified as elastic or inelastic. All right, let's go back to our information. We're looking for information about a backscattered electron. So let's scroll down. Let's look for the backscattered electron. Here we are. Right here it talks about the backscattered electron. It says some of them reflect at the same speed at which they hit. Well, if the speed after they hit is the same as the speed before they hit, then the kinetic energy must be the same, and therefore it must be elastic because there is no change in kinetic energy. So B is our answer for that one. Here we have an external magnetic field. You can see by the X's that it's pointing into the page. And then we have 5 different particles, 1, 2, 3, 4, and 5. We want to know what path 5 shows, whether it's a proton, neutron, electron, or an alpha particle. These particles well, all except for number 3 are deflected in this magnetic field, right? If it's deflected in a magnetic field, external magnetic field, we're going to use the deflection rule. So let's do this. Let's guess. Let's guess that particle 5 is a proton. If we stick our right thumb in the direction of the particle, and then our fingers in the direction of the field into the page, my palm is going to point this way. Well, a force this way is not going to cause it to be deflected this way. Looks like we guessed wrong. Okay, we're pretty sure it's a negative particle now, so let's just try that just to make sure. We're going to stick my left thumb this time, my left thumb in the direction of the particle, fingers into the page, direction of the field. My palm is going to point to the right, so the magnetic force is to the right, therefore the particle would be deflected to the right. Okay, so it has to be a negative particle. That means, since the only negative particle listed here is an electron, it's got to be an electron. We know that if that's an electron, we know that particle 1 and 2 have to be positive particles because they're deflected in the opposite direction. And particle 3 must be, I don't know about necessarily a neutron, but we know that it has to be neutral, right? It has to be neutral because neutral particles are not deflected in a magnetic field. 1 and 2 are positive, 4 and 5 would be negative, 3 would be neutral. Okay, last question. Number 5. The path followed by a moving proton, right-hand rule. In an external magnetic field, that means we're going to use the deflection rule. Is shown in which one? All right, we know the magnetic field goes from north to south. So we're going to stay right thumb into the page. Direction of the particle is into the page. Kind of a 3D diagram, but it's meant to be into the page here. Fingers go from north to south. So right thumb into the page, fingers from north to south. My palm is going to point downward. So the magnetic force is downward. A is going to be our correct answer there.